Hi, today we get to talk about this thing called the imaginary number. You might remember earlier this year, we talked about the different types of numbers that existed, like integers, rational numbers, irrational numbers, um, whole numbers, natural numbers. Basically, all of those were real numbers. And we talked about how there are other numbers that exist that aren't real. So today is the day that we finally get to talk about those types of numbers. Those are imaginary numbers. So to give you a little perspective on what an imaginary number is, we have to first talk about what we already know to be true. Here are some statements I'd like you to think about how to complete these, and I'll kind of model the first one for you. It says the square root of 16 equals blank because blank times blank equals 16. So looking at multiplication here between these. Now, in order for us to take the square root of 16, that means that we're trying to take a number times itself to equal 16. Well, we know that 4 times 4 is 16, so the square root of 16 is 4. So think about the next one. What's the square root of 49 and why? Well, the square root of 49 is 7 because 7 times 7 equals 49. How about the next one? The square root of 0. Well, let's see. The square root of 0 equals 0 because 0 times itself equals 0. All right, now how about this last one, the square root of negative 9? So we've got a negative number in the radicand. Oh, that must make this negative, right? Must mean the square root of negative 9 is negative 3. Well, if we complete the rest of our statement, that means that negative 3 times negative 3 would have to equal negative 9. Is that true? No. We know that multiplying a negative times another negative will result in a positive answer, a positive product. So that's not going to equal negative 9. All right, well then how do we do this? How do we multiply two numbers together and get negative 9? Oh, one must be positive, the other's negative. 3 times negative 3 equals negative 9. But no, that doesn't quite fit how we work with square roots, because a square root means that you have to take a number times itself. And 3 and negative 3 are different numbers. So that doesn't quite work either. So we're going to talk about how to simplify the square root of a negative number today, and that's where imaginary numbers come in. So the imaginary number, which we call I, kind of like a variable, but technically it's a number that doesn't vary. It's just a letter I. Okay, it's a number, not a variable, even though it can be confusing because it's still a letter that's used to identify what it represents. So what is I? The number I is defined such that when you square I, in other words, I times I, it will equal negative 1. So if we were to try to get I by itself here, solve the equation, undo the exponent by square rooting both sides, that's going to give us I equals the square root of negative 1. So that's what I is. I is the square root of that negative number, negative 1. So that's helpful because we are able to simplify radicals now that contain a negative number in the radicand. So here's some expressions that we can simplify. In the first row, we have the square root of negative 9. Well, we can actually split that up, kind of like we did last week or earlier in the week. Think about what two numbers multiply up to negative 9 using perfect squares. Well, I know that negative 1 times 9 is negative 9. So this is a true statement. The square root of negative 9 can be written as square root of negative 1 times square root of 9. Now we just talked about that square root of negative 1, that's I. The square root of 9, that's 3. And if both of those radicals simplify to become I times 3, we can multiply those together, kind of like how we do this with variables. A variable times a number. We put the number first, the coefficient first. So it's just 3i. It represents 3 times the value of I. So the square root of negative 9 is actually 3i. It's an imaginary number. In our next example, we have square root of negative 25. Well, let's take that -1 out of it so that what we have left is a positive radical. So square root of -1 times square root of 25. And we know that -1, or the square root of -1 is I. The square root of 25 is 5. So it becomes 5i. Maybe you're starting to develop a pattern here in what's happening. In this next one, square root of -144, if we follow that same pattern, we're just going to rewrite it by taking that positive number and the -1 and split it apart that way. And then that's helpful because we know the square root of -1 is what we're calling I, and the square root of 144 is 12, since 12 times 12 is 144. So it simplifies to just be 12i. Now I want you to look at something carefully because this is going to be helpful in really simplifying a little bit more quickly. When that number in the radicand represents a perfect square, should it be positive, it simplifies out really nicely. We know that the square root of 9 is 3, so the square root of -9 is 3i. We know that the square root of positive 25 is 5, so the square root of -25 is 5i. And as we saw in the third example, we know the square root of positive 144 is 12, so the square root of -144 is 12i. So really, anytime you see that little negative number on a perfect square, we know that since the square root of 64 is 8, this is just going to become 8i. In the next one, we know the square root of positive 4 is 2, because 2 times 2 is 4. So the square root of -4 must be 2i. And then finally, our last one, we know the square root of 81 is 9. So the square root of -81 must be 9i. So the top row, the first three ways that we did that was really just showing how we get that I as part of our simplified expression. Doing it the second way is applying what we're learning. We're seeing a pattern that's developing, and that's really going to help us simplify expressions that contain negative exponents, negative radicands. Let's also look at some of these types of expressions where we don't have perfect squares, like 18 is not a perfect square, 50 isn't a perfect square, and so on. But we can still simplify using I. It just requires us to combine what we did back on day 1 with I. So the square root of -18, I'm going to start by breaking it up as the -1 times 18 with their own square roots. I know that the square root of -1 is I, but the square root of 18 is not just a regular old number. We can see if we can simplify or split that up using perfect squares. Let's see, what multiplies up to 18? Like 3 times 6, but 3 is not a perfect square, and 6 is not a perfect square. What else? 2 times 9 is 18, but 2 is not a perfect square. 9 is a perfect square, so that'll work. So 18 was 9 times 2, so we split that up. And we know that the square root of 9 is 3. So that's going to become 3. I'm going to move the I after the 3, kind of like where we put variables after the numbers. And I always want to put that radicand, or that radical part, at the end, so it doesn't accidentally look like the 3 or the I is inside the radicand. Always put that the square root of 2 at the end there. So 3 times I times the square root of 2 is our simplified form for number 18. For the square root of -18. All right, next one, the square root of -50. Well, if we do it the same way we did the last one, let's start by splitting it up. Square root of -1, which we know is I, and the square root of 50. Well, 50 is not a perfect square, because remember, perfect squares are the ones where you take a number times itself to equal 50, and that's actually going to be a decimal value to get the true square root of 50. It's like 7.1 something, or close to 7.1. So in this one, we want to try to break it up like we did the previous one using perfect squares. So what multiplies up to 50? Well, 5 times 10. The 5 and 10 aren't perfect squares. 25 times 2, well, that'll work because 25 is a perfect square. So we break it up. We already had the I from the square root of -1. We also know that the square root of 25 is 5. I'm going to move my I after the 5 this time. I times 5 is just 5i. And I leave the radical part at the end. So 5 times I times square root of 2. All right, let's look at one more. Square the negative. I want a little bit of space. I'm going to go down to the bottom. Square the negative 60. Simplify by breaking it up. Negative 1 times 60 with the square root on each one. I know the square root of negative 1 is what we call I, but 60 is not a perfect square. Can't take the square root of 60 without getting a decimal. So we want to try to break it up using perfect square factors. So what multiplies up to 60? Let's see. I'm going to kind of go in order. 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. I believe that's it, because I can't divide 60 by 7 or 8 or 9, and then we're back to 10, like 10 times 6, 12 times 5, and so on. So those are our 6 factor pairs. Where's the perfect square? Right there. 4 times 15. So that's how we want to split this up. Square the 4, square the 15. I know that square the 4 is 2. I bring the I and put it after it, since I times 2 is 2i. And I leave the square root of 15 at the end of the expression. 2 times I times the square root of 15 is our simplified answer.